Hello friends, we will start with our first example in wave equations. In our previous videos, we tried to provide some basic logic and foundation of the topic. Now we are faced with an example question. Here, we are asked the following question. If we look here, you see an xy plane. In this xy coordinate system, the conductor shown in blue is referred to as a perfect electric conductor, abbreviated as PC. In short, there is a material here that we call a superconductor, which extends from negative infinity to positive infinity, and the question being asked is that I have set an electric field here. Its value is this. We have an incoming electric field like this. It asks us to find all the incoming and reflected electric and magnetic fields while this electric field is present. Now, if you want, let's work on how we can do this. There are a few things we need to consider here. What do we need? First, let's talk about that. First of all, we need to know how to transition from the electric field to the magnetic field. We explained these in previous examples. Of course, we will solve the Helmholtz equation to reach all the fields. In small intervals, this might be necessary, and one of the most important things is that we will apply the boundary conditions to find all the unknowns that will come from the Helmholtz equation. I will touch on each of these one by one. Let's go step by step. First, we need to grasp the logic of the situation. Now, the logic of the event is as follows. Here we have an electric field. The direction of the EZ, which is polarized with a magnitude of E0, is currently in a direction that is not visible here. It's not important. For us, it's more important to find out the magnitudes of the final fields and in which directions they are going rather than the polarization direction. Now we see where the electric field is going in this coordinate system. Let's focus on that first. Here, look at what we learned in the previous lesson. If it says e to the power of negative cky here, this means. If it says negative here, we said this means there was a positive contrast. So this is a wave going in the positive y direction. So, is it really correct? I'm looking. Yes, when I look here, y is given in this direction, the positive y direction, to the right. And our incoming field is also to the right, from left to right. It's coming towards this perfect electric conductor. It's coming towards this superconductor. Right now, I see that there is no problem here. So what do I not know here? Let me write that down. First of all, I know yi here. What do I mean by yi? It means incident in English. I know incident. I know the electric incident field. But what do I not know? For example, I don't know the incoming magnetic field. While it comes this way, let's talk about what happens after it hits here. Since a perfect electric conductor is super, it means that all incoming energy without the slightest energy loss. Theoretically. In practice, this is impossible normally. But it's accepted that way. It means that a superconductor reflects all fields, a transition to the back, what we call a resistive surface, or an impedance surface. Okay, it reflects almost everything, but here it turns into heat, losing energy in a way multiplied by a certain impedance coefficient, and those two transitions are not present here right now. The fundamental idea of a perfect electric conductor is this. If you see this patch, know that all energy reflects as it comes. Whatever amount of energy comes, its total reflects. But how it reflects, we are trying to find that out now, okay? Now look, what else do I not know? This electric field came here, hit, and reflected. I also don't know the reflected electric field, which we call the reflected electric field, of course. If I don't know the reflected electric field, then I probably don't know the reflected magnetic field either. So my goal is actually based on how I can find the other three fields, while one of these four fields is known, friends. Now, if you want, let's start with the process of finding the incident, that is, the incoming magnetic field, which you also know. We will find it using the cross operation I showed. Let's apply this. If you want in, try to reach the incoming magnetic field. Now let's start this here. Now I'm saying that my goal is to find H. And to find H. This is the formula I have for finding H. I didn't write the other one because we will use this. You know, we have the del cross H formula. Its equivalent was j omega epsilon E. If you isolate E from there, it becomes 1 over j omega epsilon del cross H. But I need to reach H right now. I need to reach HI. Therefore, I wrote the cross H formula. Now I'm writing the formula that goes to H. Now look here. I'm writing the formula that goes to H minus 1 over. Let's assume air here is air. Let's use zeros. Let's use everything for 100 lira. As long as no other epsilon is stated as 0, you can comfortably use it this way as epsilon 0. Now in my formula here, there is nu, and I will write it like this, j omega. Nu 0 del cross E. Now I feel like you are getting scared. There might be a confusion about how this cross product is done here. They don't show you this properly again in the same way. Since I know that, I will try to teach you here in a way that won't scare you again. There is a logic to it, a very nice logic, and as long as you apply that logic, you won't encounter any problems here. Now, the determinant operation is applied here, friends, like this. I will open it here, but I can't quite see how much this area will take right now. For now, I will close this part last. Okay, now the rule is this. The cross operation here is ultimately a vector operation. When we say vector, directions come into play. There are directions, right? PEC. Why? We can't perform operations without these. So, the first row here always contains the directions that are common elements of these two. So, whatever coordinate system you are in, write those in the first row, friend. So, in the first row, you write the direction vectors of the coordinate system. In order like this, let's close it from somewhere here. After closing it like this, now there are 2 rows left. From these 2 rows, you write the elements of the first one in the second row. In the third row, you write the elements of the second one. In the first row, you write the common directions of both. Now, after understanding this, how do we do it here? First of all, don't be afraid of this. This means derivative, first degree derivative. It means the derivative in all directions. Now, I have a question for you, friends, who makes up my second element here. It consists of the electric field, right? So, since this is a derivative, the part of the element that can be differentiated depends on which directions it is related to, and that is the phase part, which I will show you shortly. In those directions, there is a derivative, while in other directions, it cannot be differentiated. Now, look here. If I take the derivative of this, you might not see the CZ, because I wrote it as a vector. I'm thinking without the vector. Now, I'm performing operations on the magnitude. When you perform operations on the magnitude, what is the derivative of this based on? When you look at it, it only depends on the y above the exponent, so I can only differentiate with respect to y here. There is no derivative here with respect to x and z. This is the direction of polarization. Don't see this? You don't see this. The key point that gives the derivative here is about this exponent. Since there are no x and z above the exponent, I write 0 under x and z in the relevant directions. This means there is no derivative here. I write it like this. It is 0. It is 0. Later on, I ask if I have a derivative related to y under y. Yes, I can take the derivative of this with respect to y. I will apply the classical, simple method of taking derivatives of the exponent shortly, but before applying it, I see this. It can be differentiated with respect to y, so I just write the derivative sign. You can think only the partial derivative WRTY from the expansion of this neighbor yields something useful. You might say, nothing comes out from the others. It's a colloquial expression, but I'm saying it this way so it sticks in your mind. Later on, I look at which vectorial directions have magnitudes from the electric fields. Look, this time I'm dealing with the part of polarization. Ultimately, the polarization here, meaning this amplitude, this magnitude value, is asking which magnitudes, in which directions, and in which directions do you have the electric field. There is an electric field of magnitude E times e to the power of y in the easy direction. In which direction? In the easy direction. So, in the easy direction, it's E times e to the power of y in the magnitude of ekyp. This is not epsilon. It's a normal straight E. I have an electric field of magnitude E times e to the power of jky. So, do I have an electric field that is polarized in other directions, E in the y direction and E in the x direction, with a certain magnitude? No, I'm saying there isn't. Therefore, since I don't have polarizations in the EX direction and EY direction here either, I put 0. This is how the situation is written. So how is this process applied? The application method is as follows. You close the first one, so you close the first direction vector, then cross multiply the remaining ones and write the result. You close the second one, you multiply the remaining ones and write the result. Then you close the third direction vector, cross multiply and subtract. And by writing the remaining results in order, you reach hash. Now that we understand this, let's find this hash. Look, the most general form of hash is normally written as hash equals. In the x direction, it's hx. In the y direction, it's high. And in the EZ direction, it's hertz. This is equal to, we have a coefficient in front, like -1 over j omega, nu 0 as a coefficient. I wrote it this way, I opened a parenthesis. Now look, think of it as if you closed the first direction vector like this. Think of it as if I closed it this way. After closing it, you write this first. You say ex times the first row, since this ex is in the first row and first column, and because it's -1 in the first row, it's also in the first column. So it's 1 plus the first column. So it's 1 times the first row, first column times the remaining ones. What are the remaining ones? After closing, I look at what the remaining ones are. Del over del ye0 ej(y). I closed it, and since it's -0, you say plus. We continue normally. Look, normally, I also wrote -0. Then the process is finished for the negative part. Now think of it as if I closed the second one. Think of it as if I closed it this way, with green. What should I normally say? Plus. EY times. Since it's in the first row, second column, it's -1 to the power of the first row, plus the second column. A negative will come from here. After that, I look at the remaining ones. 0 times this, -0 times this. It came out as 0. After that, think of it as if I closed the third place this way, with purple. I was going to say plus. EZ times the first row, third column, -1 to the power of. This is fixed. -1 to the power of. I wrote all of them down, but after a while, it normally continues with the memorization method of this. Plus, minus. Plus is already a fixed rule. Look from here. -1 to the power of 2 gives plus. -1 to the power of 3 gives minus. -1 to the power of the value I will write now, which is the first row, third column, gives plus from 3. And -1 to the power of 4 gives plus. Actually, this is the source point of this. Now I continued. What was I going to write again? The remaining ones are 0 times 0 minus delta divided by delta times 0. So you see again that it came out as 0 from here, friends. So the place where I used the incident electric field on my way to HI, that is, the electric field I used, is this resulting electric field, right? Ultimately, what is this? EI. Let's write this EI down here again for us. This incoming electric field is the same time. Since I used this incoming electric field, who do I find? As a result of this operation, of course, I find the incoming magnetic field and I pay attention. In this region, there is no result coming from just high in hertz, meaning from high with EY coefficient and hertz with EZ coefficient. It comes out as 0. Let's write it this way then. High and high incident, that is, incoming equals. Hertz incident also equals 0. For example, it says to find these fields. In a way, we have actually found this. But what I will focus on is, of course, I generally look at the existing fields. And here, in the existing incident field, I see -1 over j omega 100 e to the x, -1 squared delta over delta y e to the 0 e to the minus jk. So, if we were to wrap this up, friends, the h in this expansion corresponds to hx where there is e to the minus x. So, think that the e to the minus x's cancel each other out. What remains for hx automatically? Look, this remains. Positive came from -1 squared. There is a -1 over j omega nu 0 here. It says to me here, look, take the derivative of e0 times e to the minus jky with respect to y. So, what is its derivative with respect to y, friends? Let's write this down right away. -jk. When y is constant, the numbers next to it were coming down. In front of e, you will remember. So would it be like this? -jk E0, and itself comes exactly as is, e to the minus jk, the classic derivative of the exponential. Now, I know what hx is equal to in this region, since I performed the cross-product operation here for the incoming field, meaning for y, the result I found is automatically equal to the incoming magnetic field, friends. Alright, now I will find this. We can do it like this. The j's here cancel each other out, and I take one of the necessary ones. Look, I'm taking the third one. K equals omega times the square root of epsilon nu 0. If you remember, look at what I'm writing in place of k. I say hx equals this. The negative with the negative makes a positive here, and there's no problem with that. Let's make these positive with 1 over. The negative with the negative makes a positive. What are we writing in place of k, friends? Omega times the square root of epsilon 0 nu 0. And what's down below? Omega. Now, since we have the square root of nu 0 here, I write this nu 0 as the square root of nu 0 times the square root of nu 0. I wrote it this way for better visibility. Later on, we have E0 left, E0 jki. Now at this point, the nu zeros have canceled out, friends. We need to know something here. Normally, if we divide permeability, which is the magnetic field permeability constant, by the electric field dielectric constant epsilon, we get a resistance impedance value, friends. This is generally referred to in the literature as follows. If you divide nu 0 by epsilon 0 under the square root, it is considered equal to an impedance value called Z0. Let's keep this in mind. Now that we know this, let's proceed this way on this side. Notice the square root of nu 0 divided by the square root of epsilon 0 equals the impedance Z0. But my square root of nu 0 is on the bottom, and epsilon 0 is on the top. Thus, not Z0. It is 1 over Z0. The omegas cancel each other out. I'm breaking it down step by step in this first problem solution so that you can understand it comfortably and clearly. Don't be intimidated. I'm solving it piece by piece. From here, hx equals. Look, what is E0 multiplied by the square root of N0 divided by epsilon 0 equal to, friends? It's 1 over Z0, because N0 needs to be on top. Here, it's on the bottom. So, it is equal to 1 over Z0. I multiplied this by 1 over Z0. Z0 comes down. And e to the power of negative jky. This, friends, is my incoming field. If you want to express this as a vector, it is hx, because what was the coefficient of this at the very beginning, friends? It was in the x direction. That vector sign had disappeared. I brought it back. How did I do that? Of course, by adding an ex in front of it. E0, Z0, e to the power of negative jk, y, as our hx, which is equal to what, friends? H, incident magnetic field. So our incoming magnetic field is equal to hx. What did we already know, friends? The electric field, magnetic field, and direction of propagation should be perpendicular to each other. So does this hold true. Now I have two of them clear. I'm doing a verification. Look, I'm saying, where does my electric field extend? If we draw like this for here, for example, let there be a z-axis here. For example, let this side be the positive z direction. My electric field is progressing like this in the positive z direction. Look, this is the electric field. Where is the propagation direction that we are talking about? Which way is our direction of progression? Where is this wave progressing? It's progressing in the y direction. Look, I have an electric field in the z direction. Where is the propagation that we are talking about? In the positive y direction. I have an electric field in the z direction. The direction of progression is in the y direction. In which direction did I find the magnetic field? I found the incoming magnetic field in the x direction. This also shows us the equivalence of the three, friends. Pay attention to it like this. Again, the direction of progression is this way. Propagation direction. Our direction of propagation is common. Look, this is also in RTX. Who is this? HI. As you can see, we've verified a verification. The three components are not aligned with each other. The electric field is in the z direction. The magnetic field is in the x direction, x, z, and our direction of progression is in the y direction, progressing in the y direction. We've also proven this. Friends, unfortunately, it's not over yet. Here we found H2, let's mark it. Right now, I found the incident as hx, friends, and I found everything with its magnitude value. What's left are the reflected ones, and I still haven't used Helmholtz. we have to use Helmholtz here, friends. How are we going to use Helmholtz here? Now we need to look at that. Let's solve Helmholtz. Now we will solve Helmholtz like this. Let's put a title here. Let's say Helmholtz equation. Let's not say equation anymore. Let's say Helmholtz-Dinkelme. Let's solve it. Now here, friends, we will solve the equation del squared u plus k squared u equals 0. The u here is the field you have in hand. Since we have the field now, what field do I have, friends? I have the electric field. And this electric field has a z component and an ez component. In which polarization? Since Helmholtz gives us both the incoming and reflected fields. I'm using a single general E here right now. After we find this u, we will separate the incoming and reflected ones. Okay, now, I'm saying this is the most general electric field, but I know one thing. It extends in ez direction. Alright, it extends in ez direction. And since it's not vectorial here, I will perform the operations without vectors. Okay, I will remove the vector notation and do it. And well, you need to write this down. How is the derivative Laplacian part solved? Here. To solve the Laplacian part here, friends, I need to find out which direction this function depends on. So here, first, I actually find that this function depends on y. We understand that from the phase. How does this function change according to the phase? We understand this from the phase, friends. So it's the function of whatever this equation can be differentiated with respect to. Okay, what can this be differentiated with respect to? Since it can be differentiated with respect to y, you say that this is also a function of y's dependence on y. And I will take this as y. Just to be able to perform the operation here briefly, I will know that it is already a function dependent on y. The exponential term gives me that it is a function of y, just like the differentiation here. Ultimately, whatever a function can be differentiated with respect to is actually its function. You take its derivative, accordingly. Here, we are taking the derivative with respect to y, so what matters for us is the exponent of the phase. Now, friends, we need to look at how this is done. We need to know this here. You need to remember how such an operation is solved in differential equations. If you don't remember, I will now show you how it's done. Now, first of all, don't be intimidated by this. We already know the Laplacian from our electromagnetic courses. If you have any gaps, you can watch that again. We made a video on the Laplacian gradient. It might be the 7th video. I explain how these are derived there. This derivative refers to the position. This shows that it is the second derivative of the derivative with respect to that position. We write u according to the values it depends on. Since it only depends on y here, I write it like this. I'm saying, look, let's write it like this first. I have the electric field E underscore z component in my hand. And which function does this E underscore z component depend on? It depends on y. Plus k squared E underscore z equals 0. Now I need to solve this. So how do we solve this? I write that E underscore z is a function that depends on y. Look, it's done like this. I write del squared y over del y squared plus k squared E underscore z in the places I see. The only thing I did was that. Now, after writing it this way, friends, it is solved like this. Here, we try to multiply by 1 over y. To isolate this constant, friends, this is the rule of the game. I multiply all the terms here by 1 over y. Then it becomes like this. Look at our equation. Our equation becomes like this. Something like this forms here. 1 over y del squared y over del y squared plus k squared. If we multiply by 1 over y, we get 1, and only k squared remains here. I set it equal to 0. If I multiply 1 over y by 0, it's already 0. Now, after getting it to this form, the solution in differential equations is like this, friends. If there is a constant coefficient opposite the differentiated part, it is solved by equating it. What I mean is, in order for the entirety of this equation to be equal to this term is moved across. Whatever I write here, if I add k squared to the blue part, it will obviously make 0. Of course, negative k squared. So, in a way, moving this across means I want the entirety of this to be negative k squared. Later on, I know, it might seem long right now, but if you understand the logic of the situation, you can complete this in 5 to 10 minutes. Now please try to understand the logic behind this. In fact, if you solve it for yourself from the beginning, by the end of this video, a lot will change. In this lesson, let me tell you that in advance. Now I'm continuing, and you need to know this. If the solution set of this type of differentiated equation is equal to a constant number, it is said that y is equal to this, friends. Y is equal to a times e raised to the power of alpha, like this. I don't know a and alpha. It is solved as a function related to this, or it is also called sine, or it is also called cosine. But we generally use exponential in solving these questions. I will explain why it is exponential a little later. Now I said that y would be like this. I know from differentiation. But what do I need here? Look, I need a second derivative here. So I say let me find its first degree derivative. I'm taking the derivative once. With respect to what? With respect to y. Now, friends, what is the derivative of this with respect to y? A times e raised to the power of alpha comes to the front like this. It becomes e raised to the power of alpha y. That's it. But what I need is the second derivative. So if I take the derivative of this one more time, will I reach the second derivative? Of course I will. So what is del squared y over del y squared? One more comes down from alpha, a times alpha squared times e raised to the power of alpha y. Now, after finding this, friends, I need 1 over y times the second derivative. I'm writing it like this without losing it. Look, I wrote 1 over y here, and it told me to equal it to the second derivative. I'm doing this. I just wrote 1 over y. So 1 over what did I say about y, friends? A times e raised to the power of alpha times y times this times. What did I find? For the second derivative, times alpha squared times e raised to the power of alpha. And I have written all of this in blue now. What is this equal to, friends? Negative k squared. Now, friends, did the a's go away? Did the e raised to the power of alpha y go away? What came from here, friends? It is equal to alpha squared. Negative k squared. Now, when we don't see this negative, it's the wave number. K is a positive thing. It's something like 3, 5, or 10. Now my question is this: if alpha superscript 2k superscript 2, what does alpha equal? My goal is to find this. I need to find alpha. Now let me ask you this way, so you can see it better. If x superscript 2 equals negative 9, what is x, friends? If it weren't negative, you would say plus or minus 3. But because it's negative, friends, since it's j superscript 2 1, it is plus or minus 3j. Since this is plus or minus 3j when x superscript 2 9, alpha superscript 2k superscript 2 is plus or minus kj. So it's jk, or what is the point I need to see here, friends? The root of alpha came out as both plus jk and minus jk. So what did I say y should be? I said it should be a times raised to the alpha f. Then what does y equal, friends? You write the first root of alpha, and it's a rule in this differential equation. You say plus. And instead of a, you write another new variable for the second root of alpha. So, generally, you write a times e raised to the first root of alpha, and you know that plus is usually written first. The variable related to minus jk is y, and I wrote a minus jk root in place of alpha. There was also y next to alpha, so I write that this way. It's called plus, and another variable, which I don't know, is written as a coefficient. For the second root I found, instead of e raised to minus jk, I will write plus jk this way, and by writing y next to alpha this way, I generalize y. So, is it finished, friends? Of course not. I need to find a, and b from here, somehow. I have something in mind from these, for now, but I won't tell you. It actually looks easy, but I would only find one. I know one from AB. Actually, I will mention it in the video a bit later. I definitely need to find a relationship equation between A and B here. The thing we call boundary condition comes to our rescue. Guys, the boundary conditions. The boundary conditions. We use this. We use that. We use this from the necessary ones. Now finally, we need to use our boundary condition. Guys, what we call the boundary condition is that in x, e, at y equals 0 is 0. So what does this mean? Where did this come from? The logic behind this, friends, is as follows. What do we have here that creates a boundary? We have our perfectly electric conductor. In other words, we have our superconductor. If we think of this superconductor like this, on the left side of this, we have certain fields, and on the right side, we have certain fields as well. Let's say right away that in this first part and the second part, there are fields here. There is an incoming field and a reflected field here. But because this is perfect, meaning it is a superconductor, there is no field leaking or overflowing to this side. So I'm saying that if I call this side E2 and H2, everything is zero. The fields on this side are zero. Now, the boundary condition provides me with such an advantage, what we call the boundary condition. Since we have a boundary condition, it says that when this field comes here at this 0 point, the field on the first side at this 0 point must be equal to the field on the second side. So what do I conclude from this? The result is this, friends. Since there is no field on this side and no field on that side, the field here is exactly at this boundary point. So what is our boundary point, friends? Is it x equals 0? Is it y equals 0? The perfect electric conductor, the superconductor, intersects whichever axis, meaning it disrupts a point on that axis. If you look at it, it divides exactly at y equals 0 while going along the y-axis, wherever it divides. Or another way to remember is that whatever is on top of the exponent is it, friends. The value in that region is y equals 0. We set it to 0 for simplicity in calculations. You will understand why it was set for ease of calculation later. The incoming field at this exact point must be equal to the field at this point. Since there is no field on this side, meaning E2 is 0, at the point where y is exactly 0 on the left side, it must give 0 at the transition point of both. After crossing this operation, meaning the tangent component is the maximum, it tells us that the electric field's tangent components are given. If you set y equals 0, you know you'll get 0. This is very useful for me, friends. It's very useful. Now you'll see how we will use it. Set y equal to 0. Why y equals 0? Because y is exactly the point where this perfect conductor, or superconductor, changes things along this axis. It comes from there. It's exactly the point where it intersects y. Which axis does it intersect? It intersects y. Where does it intersect? It intersects at y equals 0. That's why I wrote y equals 0. If it intersects at y equals 3, I would have to say y equals 3 here. But setting it to 0 provides ease of calculation. That's why it's generally written as 0, friends. Let's mention that too. So what is n, friends? Let's also mention n. The direction vector is the normal vector. As the name suggests, it's normal. You might know this from high school physics. Logically, which direction is our n? It's one direction. It's one of Ex, Ey, or Ez. Of course, it's in the Ey direction, friend. You can remember it by the value written here, whatever direction you took for the boundary condition. Here, we take in y. Automatically, this is Ey. Or another method to remember comes from this logic. Now, for example, this field is coming like this. Let's say this field was coming here like this. It would have a reflection like this, right, friends? If I asked you to draw a normal vector for a field that comes like this and reflects like that, where would you draw it, friends? You would say that the angle of incidence must equal the angle of reflection. And draw this right. This is what you would call the normal, right? Now, look at the direction of the normal we are going to draw. It's in the y direction. So your normal vector is one method to remember. Whatever is written is it, friends. Or another method to remember is that if you write y equals 0 here, it would be y. If you wrote x equals 0, it would be x. To avoid complicating our shape too much, let's erase this and continue. Now you understand, right? You saw that the normal vector here would be y. Now, I have this boundary condition. There is only one boundary condition. Let's title this as boundary condition and proceed. Now, friends, let's continue. I wrote this here. We said that what we call end here is the same as this, cross in the y direction. Of course, we need to know the cross product operation. I opened a parenthesis for y here in this corner, because you know that the actual notation for y is like this. In the x direction, it's as much as x. In the I direction, it's as much as I. And in the EZ direction, it's as much as EZ. And at y equals 0, this. is equal to that 0. Now, actually, it's not 0, but normally it's said that n cross e equals 0 on both sides. Actually, n cross e eliminates the first side. But since E2 is 0, meaning there's no field on the second side of the perfect conductor, I automatically write 0. Normally, these zeros come like this. Actually, Ex equals Ex2. Let's say for the second side, plus Ey equals Ey2 plus Ez equals Ez2 at y equals 0. These two are equal, but all of these here are 0. So there is no field on the second side. Therefore, in a vector equality, friends, whatever the coefficient of a direction is on this side, it is equal to that on the other side as well. Now, of course, there is also the cross product here. I forgot to write the cross product. It's the same as this, meaning Ey cross this. Here, there is Ey cross this, Ey cross this. Now, I will try to show you here that these are not important. Why is it not important? Because whatever comes here will also come there. What's important is that I need to deal with the magnitudes here. They are important to me. Normally, I will say that Ex equals 0 at 0 and Ez equals 0 at 0. But I need to show this here. Normally, how is this cross product operation done, friends? If you go in this clockwise direction, you would take the positive. If it's counterclockwise, it's negative. What is Ey cross Ex, friends? I went counterclockwise with Ey cross Ex. It gives you the third direction, as you know from the cross product operation. So what does this give us? Since I went counterclockwise, it's negative Ez times Ex. What is Ey cross Ey, guys? You know that we can't project the cross product itself, so it's 0. 0 times, so this goes to Ey. Actually, because of the 0, whatever, I wrote Ey cross Ez. What is Ey cross Ez, guys? I wrote Ex like this. Since it went clockwise, it became positive. None of this really matters. I'm doing this in this way to show that in the first question. We will solve the next questions more briefly, because you will already know some things. And Ez, where? It equals 0 at G. It equals the other side. Now, all the fields on the other side are 0, guys. Again, Ey cross Ez, E2 is 0. 0 plus 0 will come from Ey cross Ey. 0 times 0 is 0. E2 is 0. Ey cross Ey came from there as 0. Automatically, Ey came out as 0 from here. After that, it's Ey cross Ez. From Ey cross Ez, how did Ex come from here, guys? Ex came. It will come. Our magnitude is easy. But why is this equal to 0, guys? Because the fields on the second side are 0. Or let's do it this way. Let's write it neatly. Now, what I tried to show you here, guys, is that in a vector equality, the scalar multiples of the same direction vectors are equal to each other. Therefore, there is no result coming from here. These are already 0, so I won't get a result from here. I will get two results from here. Of course, E, X, and Y with negative Ez scalar multiples equal 0. The 0 on the other side, this is the first one, comes like this. And the other second one is again where the X's are opposite. Ez equals Y, which is 0. So guys, we could have done it like this briefly. What did I show here? The direction of these doesn't matter at all. Just see which area won't come here. The remaining two areas are coming. I extended this much to say that. Normally, I would have just said Ex equals 0, which is 0. Ez equals 0, which is 0, because Ey cross Ey is 0. Only Ey doesn't come here, but the remaining ones do come. Was it Ez at the beginning, or was it X? It doesn't matter. What's important is their magnitudes, guys. This is what I need. After finding these, we can now apply these conditions. So, which one will we apply it to? Let's see. Now, just a moment ago, I had a y before applying the boundary conditions. So, what was this y, guys? Do you remember? Look at what I've written here. Y was a function of Ez, so it was actually Ez, and it was all Ez total. All the incoming and reflected were all Ez. So, since this was Ez, guys, and I have Ez from the boundary conditions, I can't use it here because I don't have it in hand. Who do I have? Since it's Ez. Now let's use this. So how do we use it? We're taking this just like this, guys. Look here. It says that if you write 0 in the places where you see y in this Ez function, you can say it's equal to 0. Now, Do you understand why I divided by y at 0 at the beginning of the problem? I did it here for ease of calculation. Why? Because it tells me to go and write 0 where I see y. In exponentials, since e to the power of 0 equals 1, the calculation becomes easier. That's why I accepted to divide by y at 0. The question was posed that way so we can solve it more easily. Otherwise, as you see, this question is quite complex. Maybe it took a long time because I was trying to explain while solving it, but honestly, it took a bit longer than other questions. Now, let's continue here. It says to write 0 where you see y. Now I'm writing, and it says you can say it's equal to 0. Then I say, let's do a times this, a times e to the power of 0. Why? Because I put 0 in place of y. Plus b times e to the power of 0 equals. If it satisfies this condition, it says you can say it's equal to 0. Very nice. So what comes from here? E to the power of 0 is 1. E to the power of 0 is 1. A plus b equals 0, guys. Very nice. So what does b equal from here, guys? It's equal to negative a or equal to negative b. So, is this sufficient? I don't know a and b either. Right now, if there are two unknowns, like a and b, I would need two equations here. However, we don't need that in this question. Why? Because I actually know one of these, either a or b. I know that there is a total of the incoming and reflected areas, which are the electric fields here. And I'm looking at these in relation to the question given to me, guys. Look, there's something here. E0 times e to the power of negative ck. So, in this result, this is the incoming field. I only don't know the reflected electric field here. And I'm telling you that there is both the incoming field and the reflected field here. So, the incoming field I have is e to the power of negative ck, and a few numbers that start with e. So which one here? With negative ck corresponds to the one with a. Since there is one incoming field and one reflected field here, which one fits the format of the incoming field, friends? Here, a is in the format of the incoming field. Since it is in the format of the incoming electric field, friends, the a times e to the power of negative cky here corresponds to a times e to the power of negative cky. Our e0 here is actually our a, meaning a is automatically e0. If we found it this way, friends, then if b is negative a, then b is negative e0. So, we have found two unknown equations with two coefficients this way. Friends. Now, if I arrange e and e0, I'm organizing the y here. Look, y equals e0, which encompasses both the incoming field and the reflected electric field. What was a? It was e0 times e to the power of negative cky. What about the other one? It's negative e0 times e to the power of ck. So from here, we found the electric field, both incoming and reflected. Now, if I pull this out, friends, let's call the reflected field E reflected, since our reflected field is in the negative z direction. I wrote easy to make it vectorial. The negative comes from here, and it is e0 times e to the power of jky. Look, this way I found the reflected electric field. So what does this mean for us? Let's interpret it, friends. Notice that the negative there corresponds to the easy polarization, which is the part that creates the sinusoidal nature of the wave. So it tells us this. The wave has come here like this, friends, while rotating. It hasn't changed much, just its polarization has changed. While making an amplitude peak in the positive easy direction, it has turned and now makes the full amplitude in the negative easy direction without experiencing the slightest amplitude loss. Why? Because it reflected off a perfect electric conductor. So, in terms of magnitude, it has come with E0 power and reflected with E0 power. Again, the polarization here has turned from positive EZ to negative EZ, while coming from the positive Y direction and rotating towards the negative Y direction. This is how we make our interpretation, friends. Now, I have also found what we were initially trying to find, which is the reflected electric field. Of course, just as I was able to find the incoming magnetic field with the incoming electric field. Now that I have the reflected electric field, I can also find the reflected magnetic field. just like applying the formula from the first case. Again, let's apply what we did here, friends, if you want. Again, while having H here, let's try to reach the electric field with H in hand. Also, I want to mention something here, friends. This is the most general standing wave. The equation of a standing wave. If a wave comes and reflects with the same magnitude, the waves appear to be standing still. Another way to write this is as follows. Normally, e raised to the power of jx is written as cosine x plus j sine x, friends. Let's apply the same things here if you want. I need to show that. Another term for standing wave is also represented as sine. I need to show you how that works. Let's write e raised to the power of negative jky here. Since what's next to j goes into the cosine and sine, then whatever is next to j in the cosine here is negative ky plus j sine negative ky. Also, I need to find e raised to the power of jky. The cosine goes inside with what's next to j, k plus j sine k. And what do we have at the beginning of these, friends? There's E0 at the beginning of the negative jky's, and there's negative E0 at the beginning of the positive jky's. So if you multiply these by E0, and this one by negative E0, and then add them, how do I obtain easy? In the end, adding these two will again give us easy. Let's erase this vector for now. What happens, friends? You know that E0 absorbs the negative, so E0 cosine ky plus j E0. Since the negative can't be absorbed by sine, the negative comes out and makes it negative here, friends. Negative j E0 sine ky. From here, negative E0 cosine ky, and from here, negative j sine j. E0 sine ky. Here, E0 cosine ky and negative E0 cosine k, why cancel each other out? So, what does Ez equal, friends? It equals negative 2je0. This is also referred to as a standing wave term, friends. As you already know, sine and cosine can be transformed into each other through exponential functions in this way, or alternatively, you can transition from sine to exponential or from cosine to exponential. What do we have left, friends? With a reflected electric field in hand, let's also find the magnetic field to complete our question. I realize it has taken quite a while, but all of this is very important for understanding the logic of the situation. From now on, we'll try to solve it more briefly, without dragging it out any further. I'm trying to find the magnetic field. I have E and R. If you want, let's copy this. Now we've rewritten it this way. Our formula is clear, friends. My goal is to reach the reflected field. So, I'm saying that H, reflected, meaning the reflected, magnetic field, is equal to, here, negative 1, over j omega, nu 0, and, in the del cross H operation, I've written the direction vectors. In the first, row this way large and wide, so we can see them clearly. In the second row, the elements of the first one again have my reflected electric field, meaning the reflected electric field. So, with respect to what can I take the derivative of this? Only with respect to the exponential, meaning I only have the derivative with respect to y. So, I wrote del over del y here. I wrote 0 for the others. Del over del y is 0. I wrote 0. After doing this, friends, now which direction do I have in terms of magnitude? I'm at del cross E here. I'm in the order of E, or E. In terms of magnitude, I have E0 in the Z direction, with a magnitude of E raised to the jky. So, it means it's with respect to Z. That's why I'm writing it under Z here. E0 times E raised to the jky. I don't have polarization in other directions. There's no place where my amplitude changes. Again, if we do it this way, just like we did at the beginning of the problem, friends, pay attention that the result comes out like this. When I close E from here, when I close the others, it becomes 0. When I close this one becomes 0. So the result comes only for x. Then what do I write? HR equals negative 1 over j, omega nu 0 in the x direction. And if I multiply these by the outer terms, I get the first row. as 1. Since it's a column, you already know this. Plus, minus, plus. Since I'm dealing with this, there's no problem with the plus there either. What came, friends? Del over del y, e0 times e raised to j k y. It says to take the derivative with respect to y. Now let's do this. So what comes from here, friends? HR equals e in the x direction. Negative 1 over j, omega, nu 0 times. If I take the derivative of this with respect to y, what do I get, friends? The ones next to y. And e, 0 come like this, j, k, e, 0. And it comes exactly like this. E raised to j, k, y. It came like this. What did we know again, friends? The ones I wrote at the beginning of the problem that we need here. The third one is k equal omega square epsilon 0 equals 0. I'm writing omega square epsilon 0 equals 0. Let's write it here like this. HR equals EX times negative 1 over j omega nu 0. Substitute omega for j, k. The parts here we're simplifying. If you remember, custom times e raised to jky. The parts here were simplifying. If you remember, j with omega canceled out. It went with the square root of nu 0, and the square root of nu 0 remained here. What did the square root of nu 0 equal to? Friends, it equaled z0 impedance. But since the square root of nu 0 is at the bottom, of course, we forgot something here. We forgot this e0. Let's write it here like this, as e0. And finally, our HR will be like this, friends. In the x direction. Let's do it like this, our HR equals, friends. Since we didn't write the negative here. In this part, we also forgot the negative here as well. Since it will be negative here, it will be positive overall. It will be positive here. Therefore, this part will also be positive, friends. Since this will be positive, I can lit this part like this. It says I have a magnetic field that changes in amplitude in the EX direction with a magnitude of E0 divided by Z0. And the direction of propagation is in the negative y direction. Does that make sense? Very much so. The phase of the magnetic field didn't rotate here because normally, what did we find for the incident magnetic field, friends? Let's take a look at that. Positive in the x direction, extending in the positive x direction, progressing in the positive y direction. Of course, the electric field is progressing in the direction it is moving, which was in the positive y direction. Look, the incoming magnetic field was also progressing in that direction. Logically, since it will hit here and reflect, the magnetic field should turn in the negative y direction. When I check if it meets that condition, if you pay attention, while this is increasing, the direction is in the negative y direction, you know? Yes, it came, reflected, and continued to progress in the negative direction without changing the polarization, friends, of the E0Z0 amplitude. It was quite a lengthy problem-solving session. Let's see, in the upcoming questions, we will try to solve them more briefly. It's not an easy lesson, I hope that. If you try to solve it, by understanding it like this just once, you'll find it very beneficial. Until we meet in another video, take care.